10.3, number 36, we've got parametric equations, and we are supposed to find a Cartesian equation for a curve that contains the parameterized curve. And then, so find the Cartesian, so just involving x's and y's, and then we're supposed to figure out what portion of the graph of the Cartesian equation is traced by the parameterized curve. Alright, so unless we're dealing with trig functions, which can also be solved this way, what you're looking to do is you want to solve for t in the x equation, and then plug that t equation. So if we just look at the x equation, solving for t, e to the power, so e to the x equals t plus 1, so t is e to the x minus 1. So then we can plug that into our y equation, so y would be what we get there, squared minus 1. So that's our equation. You could expand this if you wanted to. I don't know if it's necessary, but I'll do it anyways. So I get e to the x times e to the x, which is e to the x squared, or e to the 2x, minus e to the x minus e to the x, so minus 2 e to the x plus 1 minus 1. So there's my simplified Cartesian equation. Alright, so we want to know what portion we're dealing with here. So we could look at our calculator, or we know that, well, if we look at our calculator, you could graph. Notice that we start our time at 0, so our initial point is going to be natural log of 0 plus, so natural log of 1 is 0 comma negative 1. So that's our initial, and you can see that as t goes on to infinity, it's just going to increase exponentially. But like I said I was going to do, go to mode parametric y equals, there's my equations, and if I hit graph, there's an exponential equation. Looks like it does start at 0, negative 1. If you want to make a better look at it, negative 2 to 3. If I graph that, so you can see that it's going to start at 0, negative 1, like we thought. So the answer would be what portion it would be for all x greater than or equal to 0 would be a good way of writing it.